let's review X-ray diffraction. X-ray diffraction, you have your sample, you grind it up into a fine powder, you put the powder on a stage, and the stage goes into a diffractometer. So this is the stage, and I drew our powder, this little red dust. You have an X-ray source. The most common X-ray source for diffraction is a copper source, and we call this radiation copper K alpha radiation. And we didn't talk about this here, you'll see this elsewhere, but the important thing is that this is the most common. So if no one tells you what your radiation source is, you guess that this is it. And the radiation has a wavelength of 1.54 angstrom. The source and the stage are aligned so that there's an angle theta between them, and the detector also has an angle theta between it and the stage, or an angle of 2 theta between the detector and the source. This 2 theta refers to that spacing, and when you get your results, it's going to be in the form of the intensity of the detected X-rays versus 2 theta, and basically you'll have noise with sharp peaks. Each of these sharp peaks is due to constructive interference caused by particular sets of planes in our crystal. And in class we derived how these can be related to the angle, and that comes from Bragg's law. So Bragg's law is n lambda is equal to 2d sine theta. N is a counting number, 1, 2, 3, 4, 5. Typically you pick n equals 1. That is going to be the strongest signal, and those are going to be the peaks that stand out the most. Lambda is from the radiation source. 2 is just a constant. D is the spacing between the planes. And sine theta, theta is the angle that you measured. And this is also the angle in your diffractometer. The spacing between the planes, HKL, those are the Miller indices of the planes we're talking about. Our standard notation is to use HKL to define those. It's just the nomenclature that you should know. So if you have your crystal, you've got your HKL planes, you've got your lattice. In the case of a cubic lattice, we have a lattice parameter that we call A. In the case of a cubic structure, the DHKL, cubic, is equal to A divided by the square root of H squared plus K squared plus L squared. For each of the symmetries, there's a different equation for D, and you don't need to know these for this class, but you should know in the future that if you are looking at different geometries, you're going to have to look up a different equation, and they're pretty straightforward. So what this means is it means that if you have a set of these experimentally measured planes, and you know, for example, it is cubic, and you know the radiation wavelength, then you can substitute this value into your Bragg's law, and you can use that to determine what the lattice parameter is. Or vice versa, if you know the lattice parameter, you can predict the angle where you're going to get these diffracted peaks.